Okay, well, now that Jim is here, I think we can get started. So this week, we're very happy to have Sihao Cheng, who's agreed to give this talk 2 minutes before, 2 minutes, not 2 minutes, 2 days before today. So he's filling in, so we're very thankful for that. Sihao got his bachelor's degree from Peking University and his master's and doctorate from Johns Hopkins. After Johns Hopkins, he went to the Center for Data Science at ENS, and he's now a member here at the Institute and a visiting fellow at Perimeter. Sihao is interested in many things, astrophysics, and is an expert in statistical analysis. And today he'll be talking about how to quantify textures and random fields in astrophysics.
Thank you for the generous introduction. Yeah, so I'm here last year, but I realized that I haven't really formally presented what I did in the past 2 years. So yeah, I'm very happy to have this chance today to introduce it to you. Probably some of you have seen this before, so but I did add some updates from last year, so hopefully it will not bore you. Right, so according to the great scientist Gibbs, doing theoretical science is very much about finding a viewpoint from which the world around us, complex world around us, looks simple. So nowadays, we have tons of data, right? Many of them are in, they can come from observation, they can come from simulation, they can also come from like some simplified simulations of from semi-analytical model. So many of them are in the form of the field, like data on the grid. It can be 1D time series, 2D or 3D. So to extract information from all these data is very much about like how to find a vocabulary and to map it to the physical information. So actually, we kind of see that we need a statistical vocabulary which can basically compress the millions of pixels to some much smaller compact set of numbers, so that we can do the mapping to physical information. And the first statistical vocabulary coming to mind when we talk about like a field or a time series might be the power spectrum. So it's basically the second order moment of the joint distribution of the field. It's widely used and also has different variants, right? The autocorrelation function and the power spectrum structure function, they are more or less all the same, related to some linear transformation. Yeah, so it's widely used because it's very efficient in extracting the first order information, but it also has its limitation. Right, so by the way, I want to say that when we talk about statistical vocabulary, we not only want it to be informative, but in practice, we also need it to be compact and robust. But if you, like from a field of 100 by 100 pixel, you extract like a million statistic, it's not useful, right? And also if you have a statistic, but the distribution of these statistics have a very long tail, which means like for one sample, it's not really a typical sample of this distribution, then it's not useful either. So we should keep that in mind when we choose the statistic. Right, so here I'm showing the limitation of the power spectrum visually. I think this is first probably also done in cosmology by, probably in the 90s by Alex Saleh from Johns Hopkins and some other collaborators. Right, so left-hand side is simulated density field of the universe. You see the filaments of the dark matter, and the right-hand side is a Gaussian random field. So this gives you some sense of like how Gaussian random field look like. So they look very different, which means their information, to be extracted, right? But they have the same power spectrum. So power spectrum cannot really quantify the difference. Yeah, so I just talked about some limitation of power spectrum, but you might wonder, okay, there's a natural extension of power spectrum, right? When we learn statistics, we know we have a distribution, we have like a random thing, and we take the first order moment and the expectation, the second order moment, the expectation, and we can go beyond to take like third order, fourth order, etc. Then we have more and more information, at least we believe. But I would argue that this moment expansion approach, although it's very nice analytically, can connect it to perturbation theory, to some theoretical prediction, but it is very, and it's also very useful in the basically weakly non-Gaussian regime. When the non-Gaussianity increase, at some point it will fail. And also there's another problem of the higher order moments, which is you will basically, for a field, you will have many statistics, because like for each configuration of the points, right, you have a particular statistic. So once you have like 3 or 4 or 5 points, then the number of statistics is flawed. So even if there's no other problem, still we need to think about how to combine, how to do a binning of these configurations. Right, so to show the limitation of moments here, I show a result of a very simple experiment. It's about not a field, but instead just one random variable. And we say we constrain ourselves to that it's a log normal distribution. So we have one random variable following log normal distribution. The x-axis here is one number quantifying how skewed or how non-Gaussian this log normal is. So basically log normal has 2 like parameters, right? You can do some combination, and one corresponds basically to how non-Gaussian it is. When it's 0, it's the same as Gaussian. When it's very high, then you have a skewed distribution with a heavy tail. Right, so the y-axis is showing how much feature information we can extract about these parameters. Using some statistics. So when it's Gaussian, this curve shows the second order moment information. When it's Gaussian, you use the second order to extract 100% of the information. That's expected. And when it's non-Gaussian, the information leak from the second order statistic, that's also expected. But people have a belief that if you include like all the infinite order of the statistic, you can recover 100% of information, no matter how non-Gaussian it is. But that's not true. So in reality, for the log normal distribution, you will recover 100% information when it's weakly non-Gaussian. But when it's highly non-Gaussian, you start to lose all the information. So this is some well-known results from statistics in the probably 60s. It's related to, because the moment expansion, as you know, is related to some Taylor expansion of the Fourier transform of the distribution. But Taylor expansion does not always converge, right, in the complex plane. Yeah, so that's related to that properties. Right, so this is showing that moment is not always work. Oh, it's quite a lot. Right, so today I'm going to introduce a new statistic, which is called the scattering transform, first developed by mathematicians in computer vision community. And I would say that I want to show that it's basically some tool sitting nicely in between of the power spectrum and convolutional neural net, because nowadays, like people tend to, when you have a task of random fields, people tend to use either power spectrum when it's simple, or when they say some complexity, they jump directly to convolutional neural nets. So I want to show that there's some tool kind of nicely sitting in between. And also I want to show that actually from the design, not only for the purpose, for the usage, but also for the design, there's similarity of the scattering transform between the power spectrum and convolutional neural nets. Yeah, so probably I showed this on coffee already, but I'll explain it again. So first I would like to show the visually show the power of this statistic. We do this by an image synthesis technique. So ideally, the idea is that I have a field. So the problem is, the mapping from a field to statistics usually not one-to-one, right? You have different fields with the same statistic. So then if you really want to know what the meaning of a particular statistic, probably you want to have one-to-one mapping. And you can do that with the maximum entropy sampling of the field, which means you define some statistic and then you ask what is the maximum entropy distribution of a field, given only the constraint of this statistic. So you have like more and more constraints, then you can make more and more subtle structures in the field. And the analytical result we know is that if you constrain the power spectrum alone, then you get a Gaussian random field translation invariant. Right, so this is showing the result. Like you have a weak lensing map field, you measure this power spectrum and say, I just have the constraint of the power spectrum, and you get a Gaussian field which look not the same as the original one. So that means power spectrum is not enough. That's trivial. So then you can play this trick with the bispectrum. I think there you don't have really nice analytical result, but still you can do that numerically. So this is when you measure the bispectrum and the power spectrum of the original field, say that I want this constraint and try to do some maximum entropy sampling.
Why are there four things for the? Yeah, why are there four maps in each case?
Oh yeah, sorry. So these are showing the four different sampling from this distribution. So we assume our algorithm will give you a distribution of field, and these are four samples from that distribution. Right, so you see it's improved, but still not exactly the same. Right, so then we play this trick for the scattering statistic, which is another set of statistics just, but I think visually you can see it's much better. And also I will show later an extended version of these statistics, yes.
So for the power spectrum bispectrum, are you measuring, what scales are you trying to match? I mean, are you using higher in the box?
Yeah, so we have to bin the bispectrum, and power spectrum is probably fine, but we have to bin the bispectrum because otherwise there will be so many bispectrum.
But I guess as in this example, you're trying to match the power spectrum of this over all the scales.
The overall scales, and for bispectrum is also overall scales. Yeah, but we have the rotational binning. So yeah, so we like for a particular configuration, we average overall orientations.
Maybe this is a circular question, but I mean, I certainly agree that the bottom right looks closer to the top left than the two previous samples.
Yes, you want to know how to quantify that.
Yeah, but is that,
yeah, that's a bit of a circular question because you need a powerful statistic to really quantify that. Yeah.
So here you're just trying to find something that looks, you're trying to find the statistics that are powerful enough to produce realizations that look like.
Yes. I mean, in principle, you can also check like the statistic with what you have, right? But we kind of believe the scattering statistic is more powerful than others, so it should be more sensitive in some sense. Yeah, okay. We play similar tricks to other fields and kind of find similar agreement, which is very encouraging, I think. Right, so now I'm going to go to a little detail about the design of these statistics. So I want to show you that it's just another natural extension similar to the higher order statistic, but slightly in a different way of the power spectrum. And also you can see it as a simplified version of the convolutional neural nets. Right, so the first thing I think interesting is to realize that the I mean, the definition of the power spectrum can be equivalently written in real space, right, as a convolution with a Fourier mode, and then pointwise nonlinearity in real space, which already resemble like the one layer of convolutional neural nets. But there are problems, right? If you do this, then you cannot go further again because the kernel here is totally delocalized. So once you involve with a Fourier kernel, then I mean, this is a linear transform, right? But here, if you take the modulus of this field, I mean, you don't have any structure. So if you want still some spatial information instead of just frequency information. So basically, this is about the balance between of the information, whether you want to leave it in real space or in Fourier space or in between. And that's basically lead you to a particular filter which is related to wavelets. Right. So I want to say that if you view this power spectrum by the eye of a convolutional neural net, then you find two unnatural things. One is the kernel is still localized, and the other is you have the square, but in principle, you can just have the modulus without a square. So if you do that two modification, basically you get the definition of the scattering transform. So then you see, I'll say that, I mean, you use a localized kernel first. That's something similar to a binning in frequency space, but it allows you to do localized analysis in the real space. And also you have like remove the square so that these statistics first order in some sense. So don't raise the power of the statistic so that numerically it will be more stable. Yeah, so this is basically the structure of this scattering transform. So from the original field, you basically, so the convolution, if you're not familiar, basically they are separating scales. So if you convolve a field with a particular kernel, basically you select some particular Fourier modes. So then, like you convolve it with the kernel here, it's just separation of scales. And the second part is that, I mean, the filtering itself is just linear, right? So that's not enough for statistical analysis, because if you do linear transform of a thing and then take the expectation, then you always, I mean, it's always related to just the overall mean of the field. So that's trivial. You need some nonlinearity to convert these oscillations to the amplitude of the oscillation. That's exactly what power spectrum do, right? And here it's just using a modulus nonlinearity instead of modulus square nonlinearity. So qualitatively, I say it's very similar to a power spectrum. And then you get set of fields, you take the mean of that. This is similar to some just bin the power spectrum, but it's just you bin it and you lower the power. And then the what's probably non-trivial is that you can extend this process again to the next layer, where you will have much more non-Gaussian information, because like this is similar to power spectrum, so it's more or less Gaussian information. Right, so you can see that probably that's something similar to a 4-point function, right? So it's kind of measuring the power spectrum of the localized power spectrum map to something of a 4-point. Still, I mean, the important thing is that you take the modulus, so it's always first order to the original field. Yes.
Can I just understand why it is that the modulus is more stable than, say, taking the square? I mean, I guess I'm thinking, I mean, suppose the field were very small and it's not true. So is it because you're looking at the field at places where the field is very, very nonlinear, or?
That's right. Yes. So if the field is almost Gaussian, right? Then yeah. Then
the opposite is true.
I mean, I would say both of them are stable.
Well, no, because you have some theorem that all the information is in the limit of Gaussian. You know that the best thing to do is the power spectrum. So
yes, yes, right. In terms of information, yes, second order is the optimal for Gaussian. But in terms of stability, I think the more or less same. If the original field is Gaussian, yeah.
So do you have any example in which information is missed in the power spectrum, but can be picked up by the scattering.
You mean missed in power spectrum?
Power scatter, but can be picked up by the.
Oh, I think the image I showed before about like the filaments and the Gaussian field, that's one example.
Oh, but
So every information, I mean, beyond the power spectrum, I mean, so anything doesn't look like a Gaussian texture, that will be information beyond the power spectrum.
but mathematically it's not so easy to quantify.
That's right.
Okay.
Yeah, so I think, I mean, for higher order statistics, you can show that because it's multilinear operation. You design it from multiplications, so you can show that more easily. I think one of the drawbacks of these statistics is defined with this complex modulus, so it's not so easy to derive like orthogonal information space. But numerically, you can always show that.
Oh, you made.
Yeah, okay, I'll skip this. This is just saying that there's some special thing about, I mean, wavelets is not always, it's not a random choice of kernel. There's a reason behind it. I'll still go through it. Right, so wavelet, what is wavelet? It's actually something in between of the delta function and the Fourier mode. So also its property is kind of sitting in between of real space and Fourier space. And you know that like Fourier transform is just linear transform, right? So wavelet is another representation kind of sitting in between of them. So the special thing about it is that people find if like for images like pictures of our daily life, if you do a PCA analysis and find the basis, you will actually find Fourier mode as the basis. That's because you have translation invariance. But you further ask, I want a set of bases, not only following the PCA rule, but also I want it to be sparse. Then actually you naturally get a wavelet basis, which means like PCA is the second order analysis, right? So it's using Gaussian to fit some distribution. Yeah, so in the second order, you get the Fourier modes. But if you want to consider the nonlinearity, which is more about the coherence, like structures in the field, then you find that the wavelet basis provides the clearest view of this field. And yeah, so that's about the sparsity. And people also, I mean, previously find in mammal vision system, there's some cells reacting to wavelet-like pattern, local wave patterns. And also then 10 years ago, people find in the convolutional neural nets, if you just train and learn kernel, then in the first several layers, you always find wavelet-like patterns. So there's some universality of like the wavelets. Right. I don't feel it's going into too much details. Yeah, but this is to emphasize that there's some relation qualitatively between the higher order statistic, which you might be more familiar with, to the scattering transform. So I've taught that before, so I'll skip that. But the lower panel is doing some visualization of this statistic, and again using the image synthesis technique. Oh, it's too far. Right, so here I want to show that basically the total amplitude of the statistic correspond to some structure sparsity. So if like starting from this middle field, we do the synthesis, you ask the overall amplitude of the statistic to be higher than the original field or lower than the original field, then you get a more Gaussian-like field and a more even sharper fields, right? And also because in the design of the statistic, you have, I mean, combinations of scales, right? So then you can have perpendicular scales and parallel scales. So that's the ratio between the perpendicular coefficient and the parallel coefficient will give you some morphological difference. Yes, I think this is a way to basically help to understand what the statistics do. Probably, I don't think people did this before for like even bispectrum for even 3-point function. It's only possible after these fast computation. Yes.
So for the lower right panel, so we saw many like interesting patterns there. So is it because that we already have these patterns in the data and therefore in scattering transform, they somehow choose those patterns and the rest, or it is already defined in the scattering transform?
Right. This is not a convolutional neural net. So there's nothing learned from data. This is predefined. You just predefine the kernel and all the processes. Right. So yeah. So and also these images are not from original data. They are purely synthesized.
So it's possible that does that mean that if there is some structure that's more similar to some pattern of them, they will be more sensitive for scattering transform?
Yes, you can say so. Or you can say that scattering transform have the power to like separate straight lines from curvy lines.
To related questions, what are the choices of kernels?
Well, the choice of kernel, yeah, the choice of
sensitive to the choice.
right, it's not so sensitive because anyway, wavelet will be something like it's a bandpass filter in Fourier space. So more or less they're similar. Yeah, but the particular choice, usually you want a smooth curve profile in Fourier space and real space so that you don't have artifacts. Right, so we test that for the cosmology applications. More or less there's the same.
Do you need it to decay like very rapidly at large p-values, for example?
Yeah, so the one we choose decay very rapidly at large scales.
Typically a Gaussian, for example.
Yes.
This is a dependent problems, right?
Right. So in principle, you can optimize the kernel based on your question. According
How
to
do you optimize colors? Need something.
Right. I mean, that's why I say in principle, but in practice, usually you don't need to do that. I mean, a Gaussian kernel works well.
I don't need to do that. It just seems to produce things that look correct.
No, and also like when you do a parameter inference, like in cosmology or whatever other tasks, its performance are similar. So,
Are you familiar with the JPEG format?
yeah, so that's JPEG format use some cosine transformation or wavelet transformation, depends on version, right?
So this is like that.
Yes, so not exactly. So the difference is about the nonlinearity. I mean, people know wavelet since the 90s. It's a linear transform, but it's not enough, right? If you just do linear transform, you still need to do something else in order to make it useful. Right. So the special thing about the scattering transform is it's a combination of wavelet and its nonlinearity. Right.
So is it obvious that these higher moments are actually orthogonal to each other? I mean, moments
no,
expand.
it's not.
They're not orthogonal.
I mean, when we talk about orthogonal, it depends on the distribution.
Sorry, in moments expansion, isn't that always true that they're also regardless of distribution? I'm just comparing with moments expansion.
Yeah, so in that way, it's not orthogonal.
I see.
Right.
That also is true for Gauss.
Is that true?
Yours, that is,
The moments expansion.
yeah,
Also.
I think
You mean is or is not?
is when you're computing the covariance, assuming the Gauss. But once it's a very non-Gaussian field, first of all, I don't know how you're going to compute it. So most of the time there's no answer.
Yeah. Right. So, I think I ran out of time. Sorry. Yeah, but I'll quickly show some application. Not in astronomy, but in oceanography. The idea is the satellites, right? On the sky, on the orbits, and taking pictures of the ocean. They want to measure the temperature of the ocean, and you can see the patterns of like currents and eddies, right? So here is the data set, some sample data set, basically 100 by 100 kilometer patches of the ocean, and I So I here organize these data sets very large, are millions of images. So I'm here organizing these data sets by just two numbers. One is the overall sparsity I defined previously. The other is the overall curviness of the field. So here I average over all scales, right? Because these two numbers previously depend also on scales. But I just want to say, what about, I don't care about scales. I do a very aggressive compression of the data. Can I get something meaningful? But you see that it organizes the field, the data set, I think, in a meaningful way. And in particular, if you find, right, so like the lower part, right, you have these very large eddies that we said it corresponds to like curvy structures. And if you really zoom in these regions and find what are the images in this region, they all kind of look similar, which is encouraging that this aggressive compression is useful. And actually also they are geographically concentrated in, on the Earth. So the interesting thing is people actually try to use convolutional neural nets plus like normalizing flow to find outliers in these data sets. So we are doing similar things, right? This is located in the corner of the whole distribution, which should be viewed as some outliers. They're rare and there's but convolutional neural nets somehow only pick the upper part on this plot, but they fail to really pick up these morphologically outliers. I think this is showing that it's not always, blindly using machine learning is not always the best way. If we know like morphological information is important, probably you want to inject these information. Okay, so then I'll talk about some application in cosmology. This basic idea is that in cosmology, basically we have two types of observations, right? One is about the first order quantity. So for example, the late time Hubble constant measurements from supernova, right? You directly measure the expansion rate of the universe. And another big set of observation is to measure the second order quantity or the fluctuation of the field. So there you're assuming that the universe is one realization of an ensemble of random fields. And that's why, these statistical tools become important. So these include like CFD observations and also large scale structure observations. So you're basically using the statistical property of the sum of the field to infer cosmological quantity. I'll not go through these. I think you are now all experts of gravity. So there's a weak lensing, use gravity. Anyway, I think you know that. Right, so there are like generations of weak lensing observations. Projects really focus on how to use the weak lensing cosmic shear effect to constrain cosmological parameters, because this is a neat way. You really just directly trace dark matter and don't need to care about like the bias, the conversion between galaxy lights and dark matter. So that's why people think it's a promising way to go. So the original data process, the pipeline is a bit complicated. You need to first take images of galaxies and then compile a catalog of the position and shape of galaxies. Then you basically find a region and kind of average the shape in the region. And then there's a overall distortion, shape of the galaxies on average. And you say because galaxy origin should be randomly distributed in orientations. So if you average them, still have some residual, then you assume that's caused by the gravitational lensing effect. And then basically you can have a mass map or a shear map, or you can I mean, you can work on catalogs, but they're kind of equivalent. Right, so I will focus on the last step, which is you have a map and it's supposed to be one realization of a random field and it's non-Gaussian and you want to use its statistical property to infer cosmological parameters. Yeah, so this is again very similar task. You have two fields, so these are two simulated math maps for replacing. They correspond to different cosmology, but they have the same power spectrum. And probably visually, you can also see the difference, right? These fields look like more non-Gaussian than this field because here you have more peaky things. Yeah, but to quantify the difference, you need statistics beyond the power spectrum. Right, so if you translate that difference to the constraint of cosmological parameters, then this is what usually people do for replacing. It's sensitive to a combination of omega matter and over amplitude sigma 8. Yeah, but there's a degeneracy if you only use the power spectrum because this direction is what you're really sensitive to. Because the power spectrum basically only measures the overall amplitude, but it just cannot measure how non-Gaussian, how non-linear the field have evolved. That corresponds to this direction. And if you add the scattering constraints, of course, you break the degeneracy and get a much smaller constraint. Yeah, so for comparison, I'm showing some bispectrum constraint, which is larger than the scattering constraint, which means it has fewer information, less information.
So how was this produced? These are answers from simulations. You got covariance from logs. How did you actually?
Right. So these are from simulations. These are the Fisher analysis from a set of simulations.
The covariances for the statistics, you got them by Monte Carlo.
Right. So the covariance are also estimated from realizations of simulations.
But in most of the cases, the simulations, that used to estimate the covariance, they are tailored to reproduce only the power spectrum.
These are
embodied. Sure that they're capturing the non-Gaussian statistics correctly.
These are embodied simulations, and I don't think it's tailored to anything. And also the concept here is just to show that, like for some gravity structures, you can have X-ray information. This is not yet really tailored for particular observations.
Maybe like baryonic stimulation. Yeah, like baryonic feedback or for instance interesting alignments.
Right. So I mean, this is even before.
These are not contained in MOX normally.
Yes. This is even before that. This is not including baryonic. Yeah. So we are having simulations with baryonic effects, but not yet.
So do you have any evidence that this will actually work in a realistic example?
So we are working on that actually. Yeah, so this is just showing some basic concept.
Right. Can you remind me how are the data vector in your case with the scattering transform? How are they binned and how many? How? Yeah,
so because by definition you already use the wavelet, so it's binned in. It's using some logarithmic, very wide logarithmic binning in Fourier space.
But when you do the Fisher thing, you have to assume that it's Gaussian, right? So do we know that these are well behaved in this way?
Right. So I think that's actually another advantage of this statistic. When I say like stability or robustness, that more or less mean the distribution of the statistic itself is more Gaussian. And that's true for the scattering statistics because it's first order. And for higher order statistics, it's more difficult to make them Gaussian because you multiply like 3 or 4 random variables, right? So the distribution usually of a product is less.
You're going to very small scales. I guess I mean, if I take like a Kelvin cell and then I take the absolute value of this at every point, isn't that very non-Gaussian?
It depends on, no, it's not very non-Gaussian. I mean, the most dangerous non-Gaussian thing is that you have a tail. I mean, as long as like it's I mean, restricted in the region, right? You can assume that's more or less a Gaussian. I think like, yeah, so the most dangerous thing is not that whether you have a triangle distribution or like a square distribution or whatever. The dangerous thing is that you have a distribution with a long tail. That's highly non-Gaussian.
Well, for instance, if I look at the example of the Gaussian cells, its distribution of noise is Poisson, and Poisson by definition has all cumulants. Isn't this bad for you?
I'm not sure, but I think Poisson is also have a exponential distribution. I mean, exponential tail, right? So it's not so bad.
But it has the, let's say, the bispectrum that is of the same order of magnitude as the power spectrum.
Okay.
Isn't this by definition like saying that the
I think in this case, I would still
the
say that
noise is very non-Gaussian?
yeah, I would still say that the scattering trend might be better than bispectrum because it's always making. I mean, I mean, because you don't really multiply many random variables.
I think Misha is saying that if the noise is not Gaussian, then your Fisher analysis may.
Yeah, I'm saying that noise is not Gaussian, right? But this particular statistical accounts of cells, and it's like highly non-Gaussian in the sense that the bispectrum does not suppress the bispectrum of the noise, not third moment of the noise is suppressed compared to the second moment, like the covariance, right? The skewness of the distribution of the noise is not suppressed compared to the second moment, right?
Yes.
So is this a problem?
I think in weak lensing not yet, because usually we take a pixel larger than the Poisson regime. So I mean, each pixel you have like more than 5 or 10. So then it's not so much. And yeah, we can discuss that later. Yeah, so I mean the interesting thing I want to show is that like this is the constraining power as a function of noise level. So that's what probably people care in cosmology. But the interesting thing is that like the power spectrum set the baseline where you don't have a lot of information, and then you have some other non-Gaussian ways to extract information. And the constraining power of the scattering transform seem to be parallel with another convolutional neural net result. So I think this is probably indicating that in these cosmology fields, probably you don't need convolutional neural net. It's some more advanced statistic is already enough to get all the information. Yeah, so like
you go to higher, also, like S1, S2 and higher things, it doesn't.
Right. So if you go to higher order, it's something I think the difficulty is similar to the higher order statistic. You have much more combinations of configurations, and then you need to cut. Yeah, because it will be equivalent to some like 6 point or 8 point. Right, but to get these results, right? I mean, you don't need to train like millions of parameters. You just need to compute following a strict rule, like about 40 coefficients. I think that's the advantage of traditional statistics. Right, and also we did the test for also on simulations that is not only informative but also compact and robust. Right, so going back to these experiments, you might also wonder, like in this toy model of one variable case, how the scattering transform perform, right? So I just want to explain a bit more that why these higher order moments will fail in these heavy tail distribution, because like basically the different higher order moments, they're probing different parts of the distribution, right? The mean is more close to the center of the distribution, then gradually go to the outer part. and it probes the outer part of the distribution by stretching the tail, right? But in the definition, basically you multiply the distribution by a polynomial, which will amplify the tail, and then you take the integral. So that's the definition of higher order moments. So that's why if the tail is heavy, it's not decaying fast enough, then you have problem. So for example, you have a power law tail, then at some order you will not have higher order moments anymore. But even if for log normal, you have all well-defined tail, I mean, all well-defined higher order moments, still you lose information. Right, so then the scattering transform in these one variable case is very similar to folding the core in order to probe the tail. So it wants to emphasize the tail, but you don't amplify the tail, but instead you depress the core. So in this way, I mean, that's why it will fail. I mean, it will perform much better for high. Yes.
What do you mean by folding?
Yeah, so I mean, if we follow the definition, right? So the convolution with the kernel is basically, I mean, in this one variable case, you don't have different frequencies, but instead you subtract the mean. So then it's a reason like you have a distribution. So then you find the mean and do a shift to subtract the mean. And then the modulus is something kind of folding the negative part to the positive part. Right? So then you have a distribution, like this is the original distribution. And after the first operation, you basically find the mean and fold the distribution by the mean. So then you're kind of basically folding the core region together and leave the tail unchanged. I mean, that's some analogy of these spatial statistics in this one variable case. Right, so by this, for this heavy tail distribution, log normal, which is relevant to cosmology, and probably also relevant to turbulence, yeah, so you get much more information in the highly non-Gaussian regime. And of course, I would say you will not have 100% of information because no one guaranteed that. It's not easy to derive mathematical results, but in practice, like you have much more information.
We have 10 minutes.
Okay, so quickly, I'll go through some extension of these definitions. You might already notice that in the definition of the original scattering transform, it's not full, right? So for example, it's symmetric. If it's not sensitive to the skewness of the field, if you really look at the definition, it's kind of you find it corresponds to 2-point and 4-point, but you lack some 3-point information. And also, even for 4-point, it's not complete if you really work out it. Right, so you might wonder, can you have some like lower order plus wavelet binning analogy of all the 4-point, 3-point, 2-point statistics, but not just subset of them. So that's basically what we have for the extended version. And if you just quickly go through the definition, you have a field and you do scale separation, and then you do something like a 2-point operation to take the modulus. And the scattering is to then analyze them separately. But you might wonder, what about taking the cross correlation, right, of one scale and another scale? So that's kind of natural, but that's not included in the scattering transform. So you can do that. And also we can consider the cross correlation between the original field and one of the modulus field. So let me remind you, the modulus field is similar to some 2-point quantity, and the regional field is a 1-point quantity. So if you do cross correlation of them, that's something similar to a 3-point quantity. Right, so by considering all these cross correlations, then you have like some 3-point and 4-point analogy in this scattering.
So you're no longer going to be linear in the data. I mean, it's not linear.
Yes, that's right.
Not linear.
Right. So this in some sense, you will have a second order thing. Yeah, but I mean, from the experience of power spectrum, I think like second order is still tolerable, but fourth order probably is too high. Right. So then indeed, actually, these statistics will be much more powerful. So here I'm showing synthesis results for turbulence field. This is a 2D slice of MHD simulation. And the left-hand side is simulation, the right-hand side is synthesized one. So you see that the texture looks very similar. And this is also what I showed previously for the weak lensing. Yeah, so it's much more powerful, but the drawback is then you have much more coefficients because of this cross correlation.
How many coefficients are we talking about?
So the previous scattering is several tens to several hundred, depends on what your average overall orientations. Here you can go to 10K. I mean, for 200 by 200 field, here you have 2K. So that's approaching the number of pixel, which is problematic, right? Then you're not really compressing that. Right, so I'll talk about that later. Yeah, so this is another example to show you that like if you use only the scattering, original scattering transform, you cannot really capture this cosmic web thing because like the obvious thing is skewed, right? But the scattering transform in definition is not sensitive to skewness. Yeah, but if you add just the 3-point analogy, you can make it much better. I probably don't have time for these, but this is similar interpretation of the of these, like some combinations of these statistics to try to make sense of that. And I mean, we see pretty pictures, but yeah, what I'm working on is to try to connect these structures to physical quantities. Probably there's some micro physics can be related to particular morphology of these. Right, but now last semester what I've been working on is actually about the compression of these very large statistics. So just to say it again, for these cross correlation scattering statistic, the number of statistics is approaching the number of pixels in the field, which is bad. So then what we want to do is to do some compression, right? In cosmology, usually how to do the compression, you want to cut the non-informative dimensions, right? But in order to know which dimension is informative, I mean, you need a feature analysis, you need like cosmology, you need to change cosmology and see how the statistics change. But usually I mean, you don't have so many simulations, and especially working on these high dimension space, you don't have enough simulation. So what we can do is just some approximation of that. So we can't really probe the combination of these statistics, but instead we just try to find, I mean, identify the particular statistics which might be informative enough.
5 minutes.
Okay. No, that's a detail, but somehow we get a way to cut these 10K statistics set to like about 100, and we can test whether that's a good compression by again doing the synthesis. So here is the original field, and here is the synthesis from the full set of statistics. Look very similar, but then after we do a very aggressive compression, so we have only 100 about coefficient in the set, and we do the synthesis again, and you see there's almost no difference, which means the compression algorithm here we use is very useful.
It's dependent on the realization, which ones you pick. The compression, which is just for each realization, you basically take the biggest things in some sense, or it's from the get-go.
Yeah, so you're right. It more or less depends on the realization, but if you assume one realization is already ergodic enough, then that's not.
So it doesn't depend too much on the
Right. Okay, so to summarize, I talked about different ways to extract information from random fields today. And first is the simple power spectrum analysis that's used like not only in cosmology, but almost in all statistical analysis of astronomy. And for many fields, that's the only way people analyze data, like for light curves, I think. And recently there's a rising, popular new way, which is a convolutional neural net approach, and people tend to jump directly from one to the other. And I showed today that there's the scattering transform approach, which is a more advanced statistical analysis, and nicely sitting in between of these two approaches. It's in between, not only, both in the design and also in its purpose, in its applications. So and also I showed like in one cosmology case, it can have the same constraining power or extract similar amount of information as convolutional neural nets. So you might wonder like why in this case, right, it can have a performance similar to convolutional neural nets. I think this is very much related to the some complexity of the field we are studying. So we can notice that like usually in physics, if you have non-Gaussian fields from like nonlinear dynamics, it have a complexity in between of the simple Gaussian fields and the much more complex biological world, like the image of a cat or some plants. So I think that's the scattering transform also suits these complexity of in between of power spectrum and convolutional neural nets. I think that's why I think it will be very useful in analysis of physical fields. It's really a matching between the tool and the data. Yeah, so that's all. Thank you.
So what are the kind of assumptions or restrictions that go into this? Specifically, I'm wondering, could you apply this to any dimensionality for the data? Could you apply this to a non-uniform grid or something that has maybe some missing data? What are the restrictions that go into it, I guess?
Right, for non-uniform grids probably is a bit difficult because this rely on Fourier transform. In principle, you can do that, but you need some work to really make it possible. For missing data, usually what we do is to fill the data by some Gaussian texture or some other things. Otherwise, it's like the power spectrum. If you don't do anything for the missing data, then it will be dominated. You'll see a very strong signature of the mask. So what's the first question for dimensionality? Right, for 1D, it's extremely simple. For 2D, it takes some computation. For 3D, probably is slower. I don't know whether it's useful for 4D. In principle, you can define all these things. It's similar to the power spectrum and higher order statistics. But I don't see direct useful application for 4D.
So you show the comparison of scattering transfer and with like power spectrum in that information retrieve and x-axis the from Gaussian to non-Gaussian, non-Gaussianity. Go to that plot again. So I was wondering, so let's say is there any theoretical limitation saying that given a certain statistics transform, what is the maximum performance we can do on this plot? So for example, is scattering transform like the best way that we can do, like given this safety?
Oh no, of course not. Like that's the theoretical limitation will be at 100%, right? If you are allowed to use whatever statistic. Like for log normal, we know because if you do a log transform, then they become Gaussian. So you know the best way to extract the information is to first take a log of this log transform and then take the second order statistic. Right, so when you know analytically the distribution, usually you can find some optimal way. But the problem is when you have a system is so complex that you still don't know the exact analytical expression, what do you do? So for example, in cosmology, people did try the log transform, right? Because people see like if you take the PDF of the cosmological density field, is more or less log normal. So then why not take log right first and then do the second order analysis? So people did do that. I mean, of course, in that way, the noise will be transformed in, I mean, off Gaussian. So that's the difficulty, right? So, I mean, but even in this way, you just have Poisson noise and log normal original field. It's already not easy to do it analytically.
So like I was actually confused about the one plot that you showed earlier with the shape being like you were performing better than like CNNs when the shape is like too extreme or something.
You mean here?
Like in the first part of the talk, you were showing like this multiple picture here.
Yes.
So like I mean for CNNs also like you can define the kernel to be a smaller one or a bigger one, and once you have a bigger kernel, then you can even have like the smaller shapes. So the statement you were making like you were better than CNN, that's for some specific kernel.
I think it's probably more related to how we define outliers. So these are, I'm sorry, I mean, the flavor of all these applications seem to be different from physics. It's about in practice what type of outliers you are more interested in. So the problem with CNN is that like the amplitude change of this field is huge. Those fields have like an overall variance very large. And these fields variance very small. So if you just because in order to really quantify which is outlier, which is like the typical sample, right? You need a measure of the distance from one sample to the center of the distribution, right? So yeah, so that's a problem. Here is because if the scattering transfer already encode information of morphology and it distributes the morphological information to different like statistical coefficients. So then if you work in this statistical space, you automatically have like separate different morphology. But for CNN, if you just let it to learn, then the first order thing it learn is the overall amplitude. So probably that will dominate all those other fine structures. Yeah, so it's about if you don't know any information and just let the convolution, neural network learn, usually the first order thing it can learn will cover all others fine structures.
And then one other question I had was like in your last slide, you were showing like this order of complexity. Like how do I know or how do I estimate if like scattering transform can be useful to some of the projects that I work on or something? Like for example, like this gravitation wave data with like quite a lot of noise in some cases, and so is this like among the power spectrum versus CNN? Like how do I know if this is like in the ballpark?
That's a very good question. I don't have an answer to. I think in many cases you need to try and see. We did discuss about gravitational wave data, and I think our conclusion was it's not extremely suitable, but we can discuss that later. I think so. In one hand, it's related to some entropy argument, right? These more complex fields they usually tend to have a lower entropy. But I don't have a theory for that.
Great. So if there are no more questions, let's.